quickly estimate the growth rate of recurrences just by looking essentially at a table, right? Its proof, which looks intimidating, is nothing but what we are going to do here in a pedestrian way to find the growth rate of this recurrence. How do we do it? The idea is extremely simple and logical. If t of n is equal 3 times t of n over 2 plus cn, then I can also express t of n over 2 in terms of what? N over 4, exactly. So I can unwind my, I can unwind my recurrence. So if the above is true, if I substitute n by n over 2, you will get precisely this formula. And then if you apply it to t on n over 4, you get that formula, and you keep doing that. And now you substitute all of these formulas gradually by unwinding this recurrence, right? Because the recurrence tells you how to express t of n in terms of the half, right? So first we will replace this t of n over 2 but by this expression, right? Which is the second recurrence up there, right? And then you just multiply, and what do you get? You get this, right? Because you will get 3 halves, right? It will be 3n over 2 times c, and you had cn from before. And now again, you use the very same trick. This can be replaced in terms of t of n divided by 2 cubed. Voila, here it is. Again, you multiply, and this is what you get, right? You get these terms. You now replace this with t of n over 4, and you keep doing that. Important thing. Notice that I did not bother to kind of sum up these, but I kept them in a kind of sort of form as they keep appearing. And this is very good trick when you are doing recurrences, because what are we trying to do? We are trying to see what is the pattern, right? And the pattern here obviously is that, let's move. So the same story, but on this slide, right? The story is, if I keep doing that, I will get, as you can see, this. So it's easy to see that the exponent of the 3 grows 1 by 1, right? It was 3, then 3 squared, 3 cubed, 3 to the 4th. And so do the exponents on 3 halves, right? If you pull out Cn. How far can we go? When do you hit the bottom? After how many steps? Each time you halve n. So how many steps can you make? Log n, right? Because log n tells you precisely how many times you can divide a number by 2 until you reach 1. Okay, so at the very bottom then, the exponent on 3 will be floor of log 2 of n. This will be, well, this is 1 or 2, whatever, right, depending how big is this, because integer part rounds it off a little bit. And then you have this. And then we do the same sloppiness just to irritate the mathematicians. We say, oh, well, forget about floors and ceilings. They don't change much. And you cheerfully replace these with just honest-to-God logarithms, and you don't care much that they are not integers because they are off, but by a tiny little bit. And I gave you my word that in this type of recurrences, this slightly off doesn't change asymptotic recursion. But if you want to be super precise, as in fact I think Corman and Lacerson, Rivest and Stein's book do it, you know, verifying thing is just a nauseating nightmare, really. But just your gut feeling will quickly tell you that this is all okay. Okie dokie. So now, we got this. Now, what is this? Please review. What is this guy here? Well, this is just a geometric series, right? And the sum of geometric series with quotient q is q to the power, last power plus 1. So this minus 1 will disappear. Minus 1 with q minus 1, right? So please review your summation of finite geometric progressions, right? Okay. So now, if you multiply this, you get precisely that because this is just 1/2, and it comes out as 2 on this side, and we get this. Now we do another trick that we will use very, very often. You see, we use the fact that this is true. A to the power log b of n is the same as n to the power log b of a. So the input to the logarithm can be switched with the basis of exponentiation. How would you see that this is true? What would you do? How would you prove that this is true? What happens if you take log of both sides? What is log of a to the x? It's x times log a, right? Exponent goes in front. So if I take log of the left side, I can pull out log b of n, and I get that log of the left side is log b of n times say if I take log b, it'll be log b of a. On the other side, if I take a log, I first get log b of a times log n. So they are just in switched order, but the same logarithms. All of this is in this little tiny booklet that is called Review Material. So please take a look at that because we will be doing this kind of jumbo mambo quite often. Okay, so when I switch the basis and the entry for the logarithm, I get n to the log 2 of 3 times t of 1, right? Because I have this is n divided by b to the log b of a. So this will be just t of 1. And this expression, what is log of a fraction? What is log of a over b? Log a minus log b. So this log 2 of 3/2 is actually log 2 of 3 minus log 2 of 2, which is 1. And that's precisely what you get. And if you multiply this is what you get. So you get term that is of the form constant times constant times n to the log 2 of 3 minus a linear factor. Well, log 2 of 3 is bigger than 1. So this grows faster than the linear part. So the conclusion is that the solution of the recurrence is the algorithms runs in times n to the log 2 of 3, which is n to the 1.58 and something more, right? So it's a considerable saving. This is, if n is very large, this is much smaller than n squared. And in fact, all the software packages that are capable of multiplying very large numbers, like the ones used in cryptography, they don't do it brute force. They use some of the variants of these fast algorithms. Now, how can we summarize this whole calculation? Well, it's very easy to explain this. What is happening, we did just a few very simple things. First, we are unwinding the recurrence, right? Moving from n to n half, then replacing n half with n over 4, and so forth. Then we observe how quickly the power is increasing, and we also get these sum of the corresponding linear overheads. So for even if it wasn't recurrence of the form 3 times t of n divided by 2, actually for any a and b, when you have a times t of n divided by b, you would do exactly the same. And the solution then, the final solution, will be obtained by simply figuring out who grows faster. Does the accumulation of the exponent grows faster than the accumulation of overheads, or the other way around, or are they exactly the same growth rate? So even though it's a kind of messy, in fact, very messy calculation, there is nothing much going on. When we do, next topic, the master theorem, right, we will no longer do this calculation if the master theorem applies. Now, sometimes, and we will see a simple, nice example, this kind of recipe for estimating the asymptotic growth rate will not apply. But the method of proof of the master theorem can be very slightly tweaked so that the rest applies verbatim on the particular case you have that master theorem didn't work, simply by finding how fast this guy grows and comparing it with how fast the overheads, right? Because this, what you see here, C of n, came from all the overheads. First was the overhead C times n for the additions, right? Then you had 3 times the overheads, the smaller overhead for C n over 2, and so forth. So all you have to do is you compare, you have to see, and very often, this can be explicitly summed, because either you get, usually it's reduced to some form of progression, either arithmetic or geometric progression, and it can be explicitly summed, and you can get the estimate of the asymptotic growth rate even if the master theorem doesn't apply. And that's the only reason why I ask you to actually look at the proof of the master theorem, at least the first case. There are 3 cases you will see. Look carefully just at the first case. Do not try to memorize it, because there is nothing good comes out of it. Just see what the strategy is. And there is very little going on. It's just keep unwinding the recurrence. Look how the powers in front of t of n divided by some power of the base, right? How this grows, and see if the overheads can be summed, and then you, at the end, simply compare who grows faster, this exponent on the left or the sum of the overheads, and there is nothing else to it. The rest is just to be careful when you do the calculation, pen on paper, just not to forget some term or misplace brackets and get in trouble. So this is what is our strategy. Our strategy is, first we want to see, can we speed up the process even more? We can be a bit greedy. One can argue, gee, splitting it into two pieces did the job. It increased the speed, right? Maybe splitting it into three pieces will produce even faster algorithm. But then maybe splitting it into four pieces would be even faster. And you will see something that is extremely, extremely informative, that in a sense, you do get faster algorithms, but you also don't get faster algorithms. How is this possible? Well, we will show that if you split the numbers in more and more pieces, indeed this exponent will be smaller and smaller. But remember, there are these constants in front. And the constants will be growing very rapidly. And the moral is, when you have an estimate, O, say an algorithm is O of n to the log 2 of 3, from practical perspective, this is utterly useless unless you have a very good reason to believe that the constant hiding in this O notation. What does this mean, O of n to the log 2 of 3? Essentially, this means that T of n is smaller than some constant times n to the log 2 of 3. You have to have a grasp on how big is the constant. Because if the constant is, a billion to the power billion, and you get that n is something grows with the power n to the power 1.0001. What's used that? Because for any reasonably large number, this constant in front will be just prohibitively expensive. So asymptotic estimates are good for as long as you can estimate, you can reassure yourself that the constants do not get out of hand, right? So next time we will split into more pieces, but then it will be trickier. How do you reduce the number of multiplications? And we will use something that is actually very general, and it is used in many algorithms and in signal processing. Namely, the question how we multiply polynomials. So multiplication of the numbers which naturally lead us to multiplication of polynomials, in a sense to simplify things, because polynomials have nice features that numbers don't have. So that's the first thing. And the second thing, we want to get rid of nasty calculations like this by generating just a recipe with a few clauses that in 90% of the cases, you will just say, this is case 1, this is the asymptotic growth rate. And you don't have to calculate anything. So this is what you are going to see next time. And I guess we are now out of time. So I'll see you then on Wednesday. You have your homeworks to play with over the weekend. And the weather is ugly. It's only good for problem solving.